Alrighty, this is my presentation on homework 1. So problem 1, we were given a graph which gives us position as a function of time. In the first question you ask us to describe the motion of the object. And as you can see on the graph, the object starts in the positive position or right of the origin where it stays static for 1 second and then travels at a constant speed for 3 seconds and then decreases speed where it travels at a constant rate until point D where it ends. At all points in the graph, the object is traveling at a constant speed. And you can tell that by the fact that the graph is linear at all points in time. So moving on to B, we're looking to look at the object's instantaneous velocity. At 0.5 seconds, the object is traveling at 0 centimeters per second, and that is given by just calculating the slope or rise over run, which is 0 over 1 second, giving us 0 centimeters per second. And we're able to calculate the slope the same for all 3 questions due to the fact that it is linear. And in part 2, we come to the conclusion that it's 3 centimeters per second. In part 3, we are at 1 centimeter per second. Let's see. How does the method you used to answer parts 1 through 3 rely on your answer to part A? The key part is that we know the object is moving at a constant speed. For part C, you asked us to find the average velocity of the object within certain intervals. And to do that, you will take so between A and C, we look at the object's position and time at the end point and subtract that from the first point. So we'd say the position at C is 8, and at A it was 2. So we take 8 minus 2, and we do, that gives us 6, and then we divide that by the time elapsed, which is 3, giving us 2 meters per second. And we do the same process for the following 2 problems. So part 2, we're looking at A through D. So it travels in the positive direction 6 over a time of 5. So we have 8 over 5 centimeters per second. And part 3, B to D, we see it has traveled a total of 8 over 4 seconds, giving us 2 centimeters per second. And as you can see here on the graph, I have sketched and, I have not labeled the lines. I will do that when I update. But here we have, let's see, A through C, A to D, and B to D. And the slopes, as you can see on A and C, are the same. Let's see, for each line you drew, how does the slope compare to the average velocity that you computed above? So, the slopes that we drew will, of course, be the same as the average that we computed above. In which of the cases from part C, if any, is the average velocity over an interval equal to the average of the constant velocities occurring in that interval? So, of these, I said the average velocity from C to D, which is 2 centimeters per second, is equal to the average from A to D, or excuse me, A to C and B to D. Alright, so on to the next page. It got cut off a little bit at the top, but what that's saying is that we're primarily analyzing the graph at t equals 2 and x equals 2. So our first question A, in the interval from t equals 0 seconds to t equals 6 seconds, does the object move with nearly a constant velocity or with definitely varying velocity. I wrote, the object is moving with a varying velocity. And we can see that because the graph is not linear, it is in a parabolic shape, meaning that the rate of change is constantly changing. And that can be seen here in the graph. The slope is initially negative, and as you travel, you eventually end up with a slope of 0, and it turns positive. And this graph is a mirror at 0.3, or it's symmetric about 0.3, so the slopes are opposite of one another about that point. Let's see, question B. In the small box on the graph above is a portion of the graph that corresponds to the motion from t equals 1.5 seconds to t equals 2.5 seconds. The position and time coordinates for the point in the small interval are given in the following table. Plot these points on the graph below to obtain an expanded view of the small interval. Excuse me. So there's not really a question directly relating to this, but what this shows is it's not linear, of course. You can still see that it is curved a bit, but it is more of a linear line. And on the next page, I believe we get an even more zoomed in view of that. So let's take a look. Switch pages. Okay, so the page got cut off at the top, but here we zoomed in from, it's the same graph, however we're looking at t equals 1.95 seconds to t equals 2.05 seconds, and then we plotted along. Alright, so question D. All three graphs are representations of the same motion. How can you account for the last graph being so much straighter than the first? Essentially, we're looking at a smaller slice of the graph, so we get a more accurate representation of the slope at that immediate moment in time. If we were to continue zooming in like infinitesimally, we would get like a perfectly tangential line giving us the instantaneous slope at that point. Can you tell from a very small time interval on a graph whether the motion over the whole graph has a constant velocity? And as I wrote, I'm just going to read this directly, as the measure of delta t approaches 0, it will become almost indistinguishable from a linear velocity. As I had stated before, because once you zoom in so closely, it does just give you that perfectly tangent line, as we learned in calculus when you're taking the limit. Find the average velocity over the small time interval from t equals 1.95 seconds to t equals 0.05 seconds. So what I did here, I took the final point at t equals 2.05, which I believe is 1.903, and I subtracted that. So I took 1.903, subtracted 2.103, which is the x value at t equals 1.95. And I subtracted the difference in time, which is 1/10 of a second. And that gives us, you can go ahead and calculate that out, that gives you -2 centimeters per second. And my reasoning, of course, the average velocity is a function of position relative to time, which is delta x over delta t. Let's see, and the final part. How does this average velocity compare to the instantaneous velocity at t equals 2? And here I wrote they were equal. So going back to the other graph, I did a little bit of math on this, and I calculated the equation. And sorry about that. I got P being position, P of t equals, I suppose I should have said P minus t, but I wrote x minus 3 squared plus 1. Meaning that the vertex of the graph is at 3, 1. So if we take the derivative of that, you take the derivative of that equation, it will give you 2x minus 6. And you go ahead and plug in 2 into the derivative, and you end up with -2 centimeters per second. I wasn't sure if it was actually going to show up like that, but it did work out pretty perfectly. So there you go. All right, and on the final page, once again, I cut off the top a little bit, but I have it here. An object moves along the line from point 1 to point 2 in time delta t. Question A. Suppose that the object is speeding up. Which of the labeled points A, B, or C could correspond to the location of the object at time delta t over 2? Point B lies halfway between points 1 and 2. So delta t is the time it requires to travel from point 1 to 2, and if the object is speeding up or has acceleration, it could not be greater than b. Otherwise, so just take delta t, the object would shoot past point 2, so it would have to be b if it's increasing right there. Let's see. And question B is basically just restating the same thing, but we're looking at a negative acceleration. Suppose that the object is slowing down. Which of the labeled points A, B, or C could correspond to the location of the object at time delta t over 2? So once again, basically because the object is, let's say it's got a velocity of 5 and it travels halfway, and then for argument's sake cut that in half. So if it made it to point B and you cut that in half, you'd only make it 3/4 of the way through. So it would have to be greater than B. B, of course, being halfway through. So it has to be C. And then question 4. Most cars have a speedometer, an odometer, and a clock. Describe how you could use these devices to determine the instantaneous speed of the car. So the first one is real simple because we're just looking at an instantaneous speed of the car. You can just look at your speedometer and clock, and you could just plot a function, v of t, velocity in respect to time. So you would just take a snapshot of your speedometer and your clock, and that would give you your speed at any given time interval. Question B, describe how you could use these devices to determine the average speed of the car. So in this one, you'd be looking at the odometer and the clock. So of course this wouldn't be tracking velocity, this would be looking at speed. Basically what you would do, you would reset your odometer or just keep track of your initial starting point and your initial time. And then you would travel however far, and then you take your final point in time, stop there, and your final travel time. So then you just take your distance traveled, d of t, or delta distance, and then you divide that by delta time, and you're able to calculate your average speed. Of course, units will come into play here. It depends whether you're on the metric system or whatnot. But my car would be in the imperial system, which I know you would not like. Do a little conversion and be good. But that's really it. So, hope you enjoyed. Alrighty.